Hello, my name is Luis Serrano and this is Serrano Academy. This video is about attention mechanisms. Attention mechanisms are absolutely fascinating. They are what help large language models take that extra step that helps them understand and generate text. So if you've seen transformer models lately and have been amazed by the kind of text they can generate, this is in great part thanks to attention mechanisms. And what attention does is it helps the large language model understand the whole context of the text as opposed to just a few words at a time. So at the end of the day, all attention does is a few mathematical operations on the words that can be seen geometrically, and I like to see them as words gravitating towards each other in space like planets. So in this video, I'm very excited to show you that visualization and how I understand attention mechanisms. Attention was introduced in this paper called Attention is All You Need. This paper also introduced transformers, which were a huge step in large language models. So this is going to be the first of a series of 3 videos. So this one is on attention mechanisms in a high-level pictorial way, and the next one is attention mechanism with math. So in this one we're actually going to be looking at a numerical example and going through all the formulas. And the third video is going to put all this together into a transformer models video. So here you're going to learn the entire architecture of a transformer model. So first of all, I'm very happy to announce that with Cohere we have launched a course in large language models called LLM University. I'll tell you more at the end of this video, but check out this link, llm.university. So let's get to attention. First, let's start with embeddings. Embeddings are really important in large language models. I would say that they're the most important part of large language models. And the reason is that they're the bridge between humans and computers. See, humans are very good with words and computers are very good with numbers. However, there needs to be a good bridge between them in order to communicate. This is an embedding. An embedding is really where the rubber meets the road because it's where words become numbers, and the better the embedding, the better the models are. Because if you have really good numbers for each word or for each piece of text, then the problems become much easier. So let's see an example of an embedding. Let's start with a quiz. I have a bunch of words here in the plane, so there's the horizontal and the vertical coordinate, and each word has a horizontal and a vertical coordinate. For example, banana is 6 to the right and 5 to the top, and the coordinates are 6, 5. That means it's an embedding that sends words to pairs of numbers, the pairs of numbers given by the coordinates. And now the quiz is the following. Where would you put the word apple if you were going to put the apple in this embedding over here? And I'm going to give you 3 options, A, B, or C. So think about it, feel free to pause the video and tell me where do you think you would put the word apple? And I'm going to give you the answer. I would put it on C. And the reason is because you can see that there are fruits here. On the top left you see some sports, on the bottom left you see some housing, and on the bottom right you see some vehicles. So the fruits are in the top right, so I would put the apple there. So a place like 5, 5 is pretty good for putting this apple. Obviously there are places where I could put that apple, but if I put it anywhere around the fruits, it's a good place. So that's the main thing about embeddings, that similar words get sent to similar numbers. And in reality, we're not going to have just 2 numbers per word, we're just going to have lots of them. So some embeddings have up to 4,096 numbers per word. And some embeddings are even more general. They send sentences to numbers, or they send long pieces of text to numbers, and these are called vectors because it's a list of many numbers. And you can actually go farther and see that each column actually has some property of the word. Some of them are things we know like size or color, some of them are things that are more hidden or combinations of other features that the computer has noticed. So in short, embeddings are really important. So the more work is done in embeddings, the better the language models can become. Now embeddings have some difficulties. For example, let's look at quiz number 2. We have on the top a strawberry and an orange, and on the bottom we have a phone and the Windows logo. So now you're going to tell me if things go on the top right or on the bottom left. So let's do a quiz. So you think it in your head and I'm going to be telling you the answers. Where would you put a cherry? Well, a cherry is a fruit, so it'll probably go somewhere in the top right. Where would you put Android? Well, it's a technology brand, so it would probably go close to the phone and close to the Windows logo. Where would you put a laptop? Well, it's technology, so it'll probably go on the bottom left. Where would you put a banana? Well, probably on the top right because it's a fruit. Where would you put an apple? I got you right, because apple could be the fruit, but it could also be the brand, and the fruit would go on top right and the brand would be on the bottom left. So the embedding, no matter how good it is, would not know where to put the word apple. And let's say that it puts it somewhere in the middle. And that's a problem because words can have different meanings and the computer doesn't know. Embedding just knows the word. So how would we solve this problem? Well, with attention. And here's where we get to the main topic of today, which is attention. So first, I'm actually going to tell you about self-attention, and then I'll tell you about something called multi-head attention. And basically what attention does is it uses the context of the sentence in order to help the embedding resolve these type of ambiguities. Now, in the paper that I mentioned before, attention is all you need, attention is explained using these formulas over here, using a trio of matrices called the query, key, and values, and then some diagrams like this. Now, I don't know you, but when I looked at this is the face I made. I was a little confused. Luckily, I have friends that explain things to me, so I went to my friend Jay and my friend Joao, and after many hours of asking them lots and lots and lots of questions, something made sense. And this is what I'm going to explain to you in this video. So it has nothing to do with key, query, and value matrices. I mean, it does, but indirectly, because I don't like to see matrices as arrays of numbers. To me, seeing a matrix as an array of numbers is like seeing a book as an array of letters. Books have a lot more structure than just an array of letters, and matrices have a lot more structure than just an array of numbers. And in particular, I love to see matrices as linear transformations in the plane or in a higher dimensional space, and that's how I managed to wrap my head around the attention mechanism. So what does attention do? Well, remember that the word apple can confuse an embedding because the embedding doesn't know if we're talking about Apple the brand or Apple the fruit. So what do we need? Well, what we need is the context. We need to use the other words in the sentence to tell us what we're talking about. So for example, if I say please buy an apple and an orange, you know we're talking about a fruit. But if I say Apple unveiled a new phone, you know we're talking about the brand. And what is the key that tells us that we're talking about a fruit on the left sentence and the brand in the right sentence? Well, there's normally a couple of words that help us out, and in this case, it's the word orange that helps us, because please buy doesn't mean you're talking about a fruit. You could be talking about buying a product of Apple. So it's the word orange that really helps. And on the right, it's the word phone that tells us that we're talking about a brand. So we're going to use these words to help us out. And what they're going to do is they're going to pull the word in the embedding, quite literally. That's exactly what they do. So let's go back to the embedding, and let's say that here is the word orange and here is the word phone. And the embedding, remember, that couldn't figure out what to do with Apple, so it put it here in the middle, and it doesn't know if we're talking about a fruit or the brand. So now, the word orange is going to tell us that the first apple in the first sentence is a fruit. So what the apple here is going to do is it's going to move towards the orange. So we're not going to use the original coordinates, we're going to use the coordinates that we've modified by moving the apple towards the orange. So literally, the orange pulls the apple. And when we're talking about the second sentence, Apple unveiled a new phone, then the word apple is going to be moved towards the word phone, and it's going to be somewhere around here. So I'm going to throw some numbers for explanation. They don't match the formulas in attention exactly, but just to have an idea. So if the orange is at the coordinates 11, 11 and the phone is at coordinates 1, 2, those are the numbers we use when we pass the words to the model. However, Apple is on the coordinates 6, 7, and the numbers 6, 7 are not so useful because they don't know if we're talking about an apple as a brand or as a fruit. So what we do is we modify these numbers. So in the first sentence, we're not going to use 6, 7. We're going to use this one over here. Let's say 8, 8.5. And for the second one, we're going to use, let's say, 4 and 5. And if we use these new numbers, this new vector as the embedding in the sentence, then the model is going to have an easier time. And obviously, like everything in machine learning, this process is done many times. So imagine if you do it many times throughout your model, then you're going to end up with coordinates at an apple that are very close to the orange and that it's definitely a fruit. And for the second sentence, you're going to end up with coordinates in apple that it's very close to the technology sector of the embedding. So we know we're going to deal with technology in this case. So imagine this process being done many times and the actual position of the word being moved drastically towards the region of the context of the sentence you're talking about. Now, here's a question. What about the other words? Because as humans, we know that orange is the word that helps here. But the computer can't just look around and be like, oh yeah, I think orange is the reason this apple is a fruit. No, the computer kind of has to look at all the words because it's just doing an algorithm, right? So the computer has to use all the words to modify the word apple. Now, how do we do it in a way that doesn't distract the definition of apple? Well, we put them over here, and I like to see this as gravity. So the word apple and orange are close, and so the orange is going to be pulling the apple strongly. And the other words, let's say, are far, because apple and please, or apple and buy are probably pretty far away. And so those also pull the word apple, but not so much. It's kind of like gravity, right? So when you pull it, it gets pulled more towards orange, and orange also gets pulled towards apple. All these words gravitate towards each other the way planets gravitate. So for example, the Earth and the Moon pull each other. They have a strong gravitational pull because they're close by, whereas the other planets don't pull it so much. Now here, imagine that everything has the same amount of mass. To make things simpler, and if we apply gravitation here, well, the Earth and the Moon are going to go a little close to each other, and the other planets are kind of going to go close, and yeah, Jupiter still pulls the Earth, but very little, and so on. But it's not so distracting that it will change the meaning of the sentence. So for example, the word and is not really affecting this very much because it's very far, whereas the word orange is affecting the definition of the word apple. And I like to see this as galaxies, right? So let's say that if I've been talking about fruits for a long time, because at the end of the day, you don't just use a sentence, you use the entire context. So if my context has a lot of fruits, and all of a sudden I say the word apple, well, there's like a galaxy of fruits at the top right, and it starts pulling this one quite strongly, and at the end my coordinates for apple end up really close to the coordinates for all the other fruits, because I have a fruit galaxy, because that's where I've been talking about. So in general, if you're talking about a particular topic for a while, then there's a strong heavy galaxy of words in that topic, and whatever you say will be pulled towards that galaxy, and then that's how the model keeps track of the content. And that's pretty much what the attention step does. I just like to see it as words pulling each other like gravity. However, we can do more, and I'm going to show you that next. So what I showed you is attention, which works really well. However, multi-head attention works even better. Let me tell you what it is about. So first, I have a question, a slightly loaded question by the way I ask it. Is one embedding good enough? So do you think one embedding that we use for attention is good enough to do really well? Well, it does okay, but actually no, we can do much better. We can ideally have lots and lots of embeddings, because why not? Why can't we just use 10 or 20 or 100 embeddings and combine those results? Well, that's what multi-head attention is. So let's say, for example, that you have one embedding over here, then another one over here, and then another one over here, and they all have the word for orange, the word for phone, and that ambiguous word for apple that the embedding hasn't yet figured out. So I have a quiz for you. Which one of these three do you think is the best one? Now use any criteria you would like, but which one do you think is the best embedding? Which one do you rather use if you're going to apply the attention step? And feel free to pause the video and think about it. And I'm going to tell you now. It's the first one. And the reason is because it separates the points really well. It takes that ambiguous apple in the middle and pulls one towards the orange and the other one's towards the phone, and the orange and the phone are really far away, and so therefore it manages to separate this ambiguity and send the apple in the first sentence and the apple in the second sentence to completely different coordinates. Now, from the other two embeddings, which one do you think is the worst one? Again, feel free to pause, and I'm going to tell you now. It's the second one. The second one is the worst one, because when you apply the attention step, it still can't separate the apple and the other apple very well, because that phone and that orange are not in a really good position. They're kind of close to each other, so this is a bad embedding. And the third one is so-so, because it manages to kind of separate the apple and the apple. So in general, there's going to be very good embeddings, maybe not so good embeddings, and for particular words, some embeddings may work better than others. For some topics, you could have an amazing embedding that's not that great for other topics, etc. So ideally, we want to have lots of embeddings and be able to combine them. Now, there's a small problem, is that building embeddings is a lot of work. We can't just buy them at the corner store. Research groups and companies build these really large and amazing embeddings, but they may have different sizes. That means different dimensions. So every word goes to a vector of different length, and that can be a confusion. So in reality, we can't just really take a bunch of big embeddings and combine them. It's not easy. But there's something easy we can do, which is we can have one embedding and modify it a lot and build other embeddings like that. So let me show you how. What we're going to do is linear transformations. Linear transformations is one of my favorite topics, and it's actually the way I like to see matrices. As I said before, I don't like to see matrices as arrays of numbers. I like to see them as transformations on the plane. And how do they work? Well, let's say that I have this image here of a dog, and I'm going to do several linear transformations to it. One is I'm going to rotate it some degree. Doesn't matter how many degrees, but it could be anything between 0 and 360. Another thing I can do is I can stretch it horizontally, or I can stretch it vertically. Or actually I can stretch it in any direction. Just pick your favorite direction in the plane and stretch it in that direction. And as you can imagine, these work in more dimensions as well. Here I'm doing it in 2 dimensions because the screen is flat, but you could also take something in 3 dimensions or in many more and rotate it and stretch it as you will. And there's another one called shear, which is the following. Imagine that you have, let's say, a book, and you put the bottom attached to the table and push the top of it. So it looks like this. This is called a shear transformation. And as I mentioned before, these are all represented by different matrices. Now you can combine this in any way you want, and pretty much you end up with anything like this. The way I like to imagine it is, let's look at the 2 axes, the blue axis and the yellow axis, and just send the blue axis to any other vector. Could be longer, could be rotated, could be shorter, and then do the same thing with the yellow one, and that defines that where the main square goes. And then the rest of the plane just follows this transformation, because on the left you have a plane full of little squares, and on the right you have a plane full of these parallelograms. So any transformation is a transformation for the whole plane or for the whole space. And why do we need these linear transformations? Because what we're going to do is we're going to get new embeddings from existing ones by applying linear transformations. So let's say that this is our original embedding, and I'm going to apply some random linear transformation and get this embedding, and then some other random transformation and get this embedding. Now, here is a question for you. Which one of these 3 is the best one, and which one of these 3 is the worst one? Well, just like before, the best one is the one on the right because it separates the apples really well. The worst one is the one in the middle because it doesn't really separate the 2 apples, and the one on the left is so-so. So this one over here is okay, separates them okay. This one over here doesn't really separate them, so it's a bad embedding. And this one over here is amazing because it really separates the 2 apples. So if you were to score them, let's say you give them some kind of score, and it's supposed to be high for the good embeddings and low for the bad embeddings. So let's say we're going to give the first one a score of 1, the second one a score of 0.1, and the third one a score of 4. These are just random numbers I made up, but the idea is that good embeddings get good scores, bad embeddings have bad scores. And I haven't told you how to score them. The idea is that as you train the neural network, you train these embeddings and you train their scores. And that's where the key query and value matrices come in. So now we have the big picture of multi-head attention. Here is our text, and here is our embedding. Now we're going to need to create a lot more embeddings. So the K and Q matrices are going to help us build a bunch of transformations, and the V are going to help us visualize them. This is going to be more clear on the video where I show you all the math. But for now, basically think of these as a sum. So I'm going to take each one of the embeddings, and some of them are scored with a high score and some of them with a low score. And the good ones are scored with a high score and the bad ones are scored with a low score. And so we weight them by that score. So we really take into account the good ones and don't take into account the bad ones so much. And then we add them all together. And if we add them, we get a really good embedding because this embedding has a lot of the good ones and not so much of the bad ones. So this embedding has great context. So it actually keeps track of the content very, very well. And that's the big picture of multi-head attention. So that's all, folks. Thank you very much for your attention. As I mentioned before, this is the first of a series of 3 videos. So this was the high-level pictorial attention example. But in the next one, we're going to see attention with a lot more math. So we're going to look at all the formulas, all the matrices, and also we're going to go through a numerical example explaining similarity and all the linear transformations that are happening. And finally, the third video is going to be about the entire architecture of transformer models. So if you are enjoying this, please feel free to check out LLM University. It's a course that we've created at Cohere, with two great creators, Mior Amer and Jay Alamar, and it's an entire course on LLMs with code labs, videos, and text, so I highly recommend it. And in particular, one of my colleagues at LLM University has a great video and blog post called the Illustrated Transformer. His name is Jay Alamar. You should check out all his videos. And thank you so much. So here are my coordinates. This is my YouTube channel. Please subscribe if you enjoyed this video. Put some comments or likes or share it around your friends. And my Twitter is serrano.academy, so feel free to tweet at me. My page is also serrano.academy, where you can find this video and others, including blog posts, courses, etc. And my book is called Grokking Machine Learning. You can find the discount code below if you'd like to buy it. The discount code is SerranoYT, and you can find all these links below in the description. So thank you very much for your attention, and see you in the next video.